So if we have like a non-ideal op-amp, we're going to have to like make some assumptions to make it like ideal, to make our lives like much, much easier, so we can actually analyze a circuit. The first assumption we made was that the input resistance for an op-amp must be infinite, which left us with an open circuit at the input. Let's just call this V plus, this one V negative, this is I plus, this is I negative. And there was an input resistance between like these two terminals. We said that's infinite, which made us to leave those like terminals open. If we look at it, since it is open, we have I plus exactly the same as I negative, and that is 0, right? The second assumption we made was the output resistance must be 0. So we assumed the output resistance is 0, so we replaced it by a wire. And then it was followed by a dependent source, A times V plus minus V negative, which was basically our input. Again, we made like some more assumption. And the assumption was A must go to infinity, right? And to make sure that A times V plus minus V negative is finite, we said we have to have negative feedback. And on top of that, V plus minus V negative must be 0, which led us to the second rule, which was V plus equals V negative. We talked about it. We said this equality does not mean V positive or V negative, they're 0. What it says is that like they're the same, whatever value they have. And we call this an ideal op-amp. And we call these two rules the golden rules of op-amp, of an ideal op-amp. So whenever we're dealing with an ideal op-amp, the first thing that we need to do is invoke these two rules that we have, right? What if the op-amp that we have is non-ideal? Well, these two rules do not hold. To solve a circuit with a non-ideal op-amp, we're going to have to replace the ideal op-amp with the circuit that we talked about like in the previous lecture, right? With the input resistance, output resistance, and like all those assumptions that we made, right? But as soon as we know it is an ideal op-amp, we have like these two rules. We can apply it. And then the rest is just using KVL, KCL, and whatever method that we learned to find the relationship between input and output. Oftentimes when we're dealing with op-amps, what we care about is the ratio between input and output, right? We want to know like what it is, for example, at the output with respect to the input, right? We did one example last time. I'm going to redo that example to just make sure that we are on the same page. We're going to do a few more examples to just make sure we understand how to solve any circuit with op-amps. So the first example we did last time, let's just call it example 1, was an inverting amplifier. The circuit looked like this. We had some input voltage, which we knew what it was. It was connected to the ground. And then we have some resistance R1 that goes to the negative side of the op-amp. The positive sign, the positive terminal goes to the same ground. And then we have some R2. And if I look at like the voltage here, that is V out, which is positive and negative. Right? We talked about like this circuit, and we said like all these grounds are the same thing, right? Basically what it means is that the entire circuit down here is connected to our ground. Right? But we're just not writing it because we want the circuit to look a little like more professional and nicer, right? But what it basically means that whatever I have down there is connected to the same ground, right? And the question's asking me like, what is V out? or what is V out over Vn, right? Let's assume this op-amp is ideal. To be able to apply those golden rules, I have to check if the circuit is negative feedback. It is indeed negative feedback because the output here is actually going to the inverting terminal of my op-amp, right? So it is negative feedback op-amp, and at the same time, it is an ideal op-amp, so I have like those two rules. So let's call this guy over here V negative, this guy over here V positive. Current through this I negative, current through here I positive. Golden rule number 1 tells me I plus must be the same as I negative must be 0. Right? That was our first rule. Golden rule 2 tells me V negative is the same as V positive. But if you look at this circuit, what is the value of V positive? What is it? V positive is connected to the ground. So what is the value? It's 0. Right? So that equals to 0. Keep that in mind. This 0 is different than this 0. This 0 is due to properties of the op-amp that we have. This 0 is just because this V plus is connected to the ground, right? Let's call current through R1 I of R1. Do you agree if I have voltage across a resistance, I know current through, right? We have Ohm's law, right? But what is voltage across this R1? Well, at this node, I know the voltage at this node. What is it? That's Vn. So what is voltage across this R1? It's Vn minus V negative, right? So if I divide this by the value of the resistance, I get current through it, right? So I have I through R1, and again, that's due to Ohm's law, is voltage across it, which is Vn minus V negative divided by R1. Right? That's Ohm's law. But what is V negative? Look at the second golden rule. It tells me it's 0. So this guy over here is 0. So I through R1 is Vn divided by R1. Right? We know that. What I'm claiming here is that whatever current I have through R1 is the exact same as current through R2. Let's just call it I of R2. Why is that? Well, let me write a KCL at this V negative node. So KCL at V negative. What do I have? Whatever current that's going in must be the same as whatever current that's going out. So I through R1 should be I negative plus I through R2. Right? But what is I negative? It's 0. Therefore, I through R1 is exactly the same as I through R2. Right? What does that tell me, though? What it tells me is that if I have this I of R1 going into this node, there is going to be no leakage of current through this branch, and whatever current I have here is going to pass through this R2. Right? And if I know current through R2, what do I know about it? I know voltage across it. So if I compute voltage across R2, voltage across R2 is R2 times I through R2. Right? Again, that's Ohm's law. But what is I through R2? That's I through R1. Right? We already computed I through R1. What is it? It's Vn divided by R1. So if I sub it in here, that is R2 divided by R1 times Vn. right? But look, V across R2 is also V negative minus V out, right? That's voltage across it. So that is V negative minus V out. Again, golden rule of op-amp tells me this V negative must be 0. What do I have then? I have R2 divided by R1 times V in equals negative V out. So I know exactly what V out is. V out is negative R2 over R1 times V in, right? If I want to find the ratio of out to in, that is minus R2 divided by R1. Which basically means this resistance over the input resistance R1 with a negative sign, right? And what it means is that if R2 is huge, what happens? It means output is going to be amplified by this number, but with a negative sign. So it inverts the input, right? If R1 is much bigger, it means my output is roughly 0, despite the fact that the input could be anything, right? But the whole idea is that since I have this negative sign, it inverts like whatever sign the input has, right? Any question on this? Is that clear how we approach this problem? Again, the first step is always to check if it's ideal op-amp. If it's an ideal op-amp, we have those two golden rules. We're going to write it down, and we're going to write KVL and KCL. And while we're writing the KVL and KCL, we're going to use those two, right? Let's do another example. Example 2. This is called non-inverting amplifier. What it looks like is that I have my ideal op-amp. The positive sign this time is connected to some source V in. The negative sign is connected to some resistance. Let's just call it R1. And then I have that connected to the output with a resistance R2. And that is V out. Right? Again, what I'm trying to do is to find the ratio between output and input. Right? Looking at this circuit, well, we already said it's an ideal op-amp. And we know it's negative feedback because there is a feedback from the output to the inverting terminal, right? Since it is an ideal op-amp with a negative feedback, we have the golden rules. So what are the golden rules? Let's call this one over here V plus, this one over here V negative, the current here I plus, the current here I negative. What are my golden rules? The first one is V plus must be the same as V negative, right? That's the first golden rule. But what is V plus? What is V plus this time? That's V in. That's exactly V in, right? So it's V in. Therefore, V negative must be V in, right? The second rule tells me I plus is I negative, and that's here, right? These are my rules. Obviously, I can do whatever I did in the previous example. I can just say current through R1 is exactly the same as current through R2, right? And find current through like one of them, and then write basically like voltage across the other one, and find the relationship between output and input. I can do that, right? I'm not going to do it. I'm going to just solve it in a different way, but I highly encourage you guys do as we did in the previous example. I'm going to try to solve this problem with a simple observation. Do you agree voltage at this node with respect to the ground is V out? That's what we called it. And do you agree this ground is exactly the same as this ground? It's no different. Therefore, do you agree voltage from here to this ground is V out? Right? If I just show you that R1 and R2 are in series, do you agree I have a voltage divider? Because what it says is that voltage from here to here is V out, which is voltage across these two. And I can find voltage across every single one of them that I want. Right? But look, I am claiming R1 and R2 are in series. Because if I look at this I negative over here, this I negative is 0. So whatever current that I have going through R1 should go through R2. So it is indeed a voltage divider circuit. So let me just quickly remind you what a voltage divider circuit was. Reminder, if I have a circuit, let's just call this one R1, this one R2. This is Vs. I can find voltage across R1 as R1 divided by R1 plus R2 times Vs. Voltage across R2, R2 divided by R1 plus R2 times Vs. Right? Let's call this one like V of R2, for example. Right? If I want to apply this to this guy, what do I have? What is my V out? V out is voltage across both of these. Right? Therefore, that's my Vs. What is voltage across R1? That's this V negative. Right? Therefore, if I apply voltage divider, what do I have? I have V negative equals R1 divided by R1 plus R2 times V out. But what is V negative? We just said V negative is like V input. So this guy is V input. And this is due to the golden rule. Look what I have. I have the relationship between input and output. Right? I can find V out, which is basically R1 plus R2 divided by R1 times V in. I can also find the ratio, which is 1 plus R2 divided by R1. Remember, this guy over here is 1 plus R2 over R1. Right? Again, you can do whatever we did in the last example, right? You can find current through R1, and then you can say that current is exactly the same as current through R2, and do exact same as what we did before. If you do that, you're still going to get the same answer. But I just wanted to show you another way of thinking about this problem. Right? I highly recommend you guys do that method as well to see if you can get the same result. It's a practice. Any question on this? Any question on this? Is that clear how we approach problems like this? Yes? Let's do one more example, which is kind of the generalization of the first problem we did. Let's just see how. So this was the second example. Let's do another one. Example 3. This is called summing amplifier. Which again, as I said, that's kind of the generalization of the inverting amplifier. And you're going to see why. Well, let's just say I'm given this circuit. This is the positive, this is the negative. Positive is connected to the ground. Negative is connected to a resistance here. Let's just call it R1 with some voltage source VN1. Also connected to another resistance R2 with another voltage source VN2. I like another one. Let's just call it VN3. And this guy is connected to some other resistance R, which is connected to the output, and this is V out. Right? Obviously, if we didn't have like these two, this one was exactly the inverting amplifier. But let's just find the relationship between inputs and the output, right? And see if it is actually the inverting amplifier or not. Again, all these op amps are ideal op amps. And if I look at the output, it goes back to the inverting terminal, which is the negative side. So it's a negative feedback as well, right? If it's a negative feedback, I have the golden rules, right? So I have the golden rules. What is the golden rule? Let's call this one over here V plus. This one down here V negative. First one that tells me V plus is exactly the same as V negative. But what is V plus? It's 0. It's connected to the ground. So it is 0. The second one tells me I plus, which is this guy, is the same as I negative, which is this one. And that is 0. Right? This is just the golden rule that we have. Let's call current through this one I of R1. Do you agree I of R1 is voltage across R1 divided by its value? That's Ohm's law, right? What is voltage across R1? That's VN1 minus V negative, because at this node I have V negative, divided by R1. You with me? What is V negative? That's 0. So that is VN1 divided by R1. Right? How about I of R2, which is current through R2? Again, that's voltage across it divided by its value. Do you agree this is still like V negative? This guy over here is also V negative. Do you agree with me? Yes? Why? It's just a wire, right? There is no potential difference. So what is voltage across R2? It's VN2 minus V negative, right? So I have VN2 minus V negative. If I divide that by its value, I can get current through it. With the same logic, since V negative is 0, this guy is VN2 divided by R2. This is 0. How about I through R3? Do you agree this node over here is also V negative? Again, there's just a wire. So there's no potential difference. What is the voltage here? That's V in 3, right? So voltage across R3 is V in 3 minus V negative divided by the value of the resistance. This is 0. Therefore, this is V in 3 divided by R3. Right? Let me call I through this R over here, I of R. Do you agree I can write I of R in terms of I of R1, I of R2, and I of R3? I can, right? I just need to write the KCL at this node. Right? So let's just call it like node 1. Right? So KCL at node 1. What does it tell me? It tells me whatever current that's going in must be the same as the current that's going out. What are the currents that are going in? So I have I of R1 that's going into node 1. I have I of R2 that's going into the node 1. And I have I of R3 that's going into the node 1. And I have I of R and I negative going out. Right? But this I negative is 0. So there is no leakage of current over here. So whatever current I have through R1 is just going to flow through this node, added with this I through R2 and I through R3. Right? There is no leakage of current. But what was I of R1? We just computed it. It's Vn1 divided by R1. So I have Vn1 divided by R1 plus I of R2 as this guy. So it's Vn2 divided by R2 plus Vn3 divided by R3. And that must be I through R. Right? What is I through R? It's voltage at this node minus voltage at this node divided by its value. Basically, voltage across R divided by its value. But what is voltage at this node? What is voltage at node at N1? This is V negative. Right? So I have V negative minus V out divided by R. What is V negative? 0. What do I have? I have V in 1 over R1 plus V in 2 over R1 plus V in 3 over R3 equals negative V out divided by R. I can find V out. V out is negative R times V in 1 divided by R1 plus V in 2 divided by R2 plus V in 3 divided by R3. And as you can see, it is basically 3 inverting amplifiers. They're added together, and hence the name, summing amplifier. Right? If I didn't have like these two, this was exactly the inverting amplifier that we talked about. Basically, the first example we did. But over here, we have like 3 of them, so they're all like added up. Obviously, I can generalize this to n of them. Right? I can generalize it to whatever number I want. And I get the same exact number. Right? And the approach is the same way. Right? Any question on this? Is that clear how we're doing this? Yes? You guys back there with me? All right. Let's make it a little more interesting. Let's make it a little more interesting to see if we can solve it. Let's just say my circuit is this guy. Example 4. let's just say I have some circuit over here that I don't really care about, but I know the input current is I input over here, and I know this side of it is actually connected to the ground. I'm going to feed this to an op amp. This is a negative side, this is a positive side, and I'm going to hook up the positive side to the same ground. Then I'm going to have some resistance over here, right? Then I'm going to hook this up to like another op amp. This time this is positive, this is negative, right? And it basically is connected to like a resistance RL and resistance RI, and this is connected to the ground. And let's call this I out, right? This current here is I out, basically the current for this. The question is asking me what is I out over I in. Right? What's going on in this circuit? I have two op amps. I'm assuming both of them are ideal op amps. If both op amps are ideal, I still have my golden rules for every single one of them. If I have 10 op amps in a circuit, I can still write golden rules for every single one of them because they're ideal. And I know like both of them are like negative feedback, right? Because the output of like one of them is actually going back to the inverting side. Both of them are negative feedback. So let me just write the golden rule for the first op amp. Let's call this like the first op amp, and this is my second. So golden rule for the first one. Let's call this one V negative, call this one V positive, this one I negative, and this one I positive. What do we know? The first rule tells me V plus must be the same as V negative, and that's equal to what? 0, because V plus is connected to the ground, right? So this guy is 0. Second rule tells me, regardless, I plus is the same as I negative, and that is 0. Right? What does this rule tell me? What is that I plus is the same as I negative equals 0? Tell me. It tells me whatever this input current is going to flow through here, and it's going to be the current through this RF. Right? Why? Because this current is 0, so there is no leakage here. So whatever current I have here is just going to pass through here. You with me? Yes? If you don't see it, you can always write a KCL at this node. And whatever current that's going in must be the same as whatever current that's going out. And you get the same thing. Because this I negative is 0. So this guy tells me I input is exact same as I through RF. You with me so far? I can write the exact same thing for the second op amp, right? I have the golden rule. So let me just do that. So golden rule for the second one. Let's call this one V prime plus, and this guy over here, V prime negative. This one I prime positive and I prime negative. Right? Just a name, right? You can call it like I2 or whatever. What does the golden rule for the second op-amp tell me? It tells me V prime positive must be the same as V prime negative. That's what it tells me. It tells me nothing more than that, right? It also tells me that I plus prime is the same as I negative prime, and that is 0. That's what it tells me, right? Let's call current through this Ri, I of Ri, right? What I'm claiming is that I can compute this I of Ri. What is I of Ri? Well, I got to know voltage across it. And if I know voltage across it, I can divide it by its value. Then I know current through it. But what is voltage across this? Well, what is this node? Do you agree this node is exactly the same as this V prime negative? So what is voltage across this? That is V prime negative minus 0 divided by Ri. Right? But keep that in mind. All I'm trying to do is to find the relationship between the output and the input. Right? So I got to somehow write everything in terms of this input. So if I have this V prime negative, if I want to somehow connect it to this guy, I have to go back and write it in terms of this V prime plus, because this V prime plus is the output of like the first op-amp, right? So I can rewrite this as V prime plus divided by Ri. Why could I write this as V prime plus divided by Ri? That's the first rule that we have for the second op-amp. That is basically the first rule that we have over here, right? That tells me like V plus prime is the same as V negative prime, right? What else do we have? What I'm claiming here is that this I out is exactly the same as this I through Ri. Why? Because this is going to be I out. This is I out, right? It gets to this point, and it splits between here, this branch, and this branch up here. But this branch up here has no current flowing through it. So whatever I have here is just going to flow through Ri. So let's just call this node V prime negative. So writing a KCL at node V prime negative tells us whatever goes in should come out. So I out equals I through Ri plus I prime negative. But this guy over here, we know it is 0. Therefore, I out is I through Ri. Right? Right? Do you agree this Ri here is the exact same as this Ri up here? Right? Therefore, I out equals V prime positive divided by Ri. Right? So voltage across so let me just call this equation 1. So using equation 1, we have I out equals V prime plus divided by Ri. Therefore, V prime plus is Ri times I out. right? Do you see it? Do you see it? Let's go back to the first op-amp. Let's go back to the first op-amp. What is voltage across RF? Do you agree that's RF times current through it? So that is RF times I through RF. But we know I through RF is exactly IN. It's right here. That was due to that golden rule that we have. You agree with that? I'll write it as RF times IN. Right? But is there like another way that I can represent this V across RF? Well, I know the node voltages, right? I know that's V negative minus V prime positive, right? I have the node voltages. If I subtract them, that gives me voltage across that element. So this guy is also V negative minus V prime plus. But what was V negative? That's 0. What was V prime positive? We just computed it. That is, therefore, negative Ri times I out. Look what I have. RF times I input equals negative Ri times I output. Therefore, I can compute, let me just write it down. RF times IN equals negative Ri times I out. If I want to find the ratio, that is negative RF over Ri. Right? Yes. Sure. So let me explain this one more time, because that's quite complicated. And if you understand this one, we pretty much can solve any op-amp, right? We have two op-amps. Let me just move this a little down. We have two op-amps, right? Both are ideal op-amps, right? Which means golden rules apply to both, right? What are we trying to solve for? We're trying to solve for the ratio between output and the input. So we somehow need to write our output in terms of the input. So we have to like find the connections, right? The first step is always to write the golden rules, right? If I write the golden rule for the first one, I know V plus must be the same as V negative. And because the V plus is connected to the ground, it is 0. Regardless, I plus is always the same as I negative, and it is 0. So that's the first golden rule. Looking at this golden rule, I can immediately see there is no current leakage over here. Therefore, whatever current I have going into this node must flow through this RF. Right? There is no leakage here. And I have this guy. I can do exactly the same thing for the second one. I have V prime plus to be exact same as V prime negative. That's our rule. We also know I prime plus must be the same as I prime negative, and that must be 0. Right? Immediately after like assuming these two things are 0, what we know is that if I look at current through this RL, must be the exact same as current through this RI. Because there is no leakage here. right? If we cannot immediately see it, we can just write a KCL, right? So I know current through this is exactly the same as current through this. So I can find voltage across this Ri. If I find voltage across this Ri is exactly the same as this V prime plus. And that's due to the first rule that we have over here. Because this guy tells me this V prime negative, which is exact same as voltage across this Ri, right? And that tells me like exactly like what this V prime plus is. As soon as I know V prime plus, I know voltage across this RF. That's V minus minus V prime plus, right? We also know voltage across this is current through it times its value. If we equate these two equations, what we're going to get is the relationship between input and the output, right? So the entire idea here is that we're going to write down the golden rule, and the rest is just writing KVL and KCL. And see like the connections. That's the whole idea. Any question on this? Is that clear to everybody how it works? So what we're going to be doing like next lecture, we're going to do like one more example on op amps to cover like everything. And then we're going to talk about like another method to simplify down the circuits, basically to circuits that we already know, a voltage divider or a current divider. And if we're able to simplify down any circuit to those two simple circuits, we call it like Thevenin or Norton equivalent circuits. So that's what we're going to be doing next lecture. All right? Any question? So please take a